Hello everyone, welcome to this lecture. Just to recall, in the last lecture we have introduced a new cryptographic primitive, namely cryptographic hash functions, and we also discussed rigorously one of the important security properties that we require from cryptographic hash functions, namely that of collision resistance. We also saw how to construct cryptographic hash functions using Merkle-Damgard paradigm. So, the plan for this lecture is as follows. We will see how to use collision resistant hash functions to design message authentication codes for arbitrarily long messages, and we will see an instantiation of this paradigm, practical instantiation, namely HMAC, which is a widely used message authentication code used in practice. So, just to recall, we have already seen how to construct message authentication codes for long messages. So, recall the construction of our PRF F star using the CBC mode of PRF for fixed length inputs, and this PRF F star based on CBC mode takes inputs as binary strings of arbitrary length and gives you a tag or an output of fixed size. So, just to recall how exactly this construction F star looks like, it takes an input which is a key of size n bits, and the actual input on which the PRF needs to be evaluated, which can be a bit string of length up to n times L bits, and it gives you a fixed output of size little n bits, right. And basically, depending upon whether the underlying message on which you want to evaluate this PRF F star is a multiple of n or not, we actually divide we are actually having one of the two possible cases. So, the first case is when the number of blocks right in your message on which you want to evaluate your PRF F star, it is already a multiple of n. In that case, what we do is we first apply a prefix free randomized encoding operated by a key k1, and once we have the prefix free encoding of your message on which you want to evaluate your PRF, what we do is basically we evaluate the CBC mode of PRF which is block wise secure, and where the number of blocks in the encoded input m is already a multiple of the block size of your fixed size PRFF, and this we operate using another key k0, and the overall output is taken as the output of your PRF F star for the input m. This is for the case when the size of your message is c times some n for a constant c. Whereas if the size of the message is not a multiple of n, then what we do is we do a padding before computing the encoding of your message. So, the padding is a deterministic padding where we divide your message into blocks of n bits, n bits, n bits, and the last block basically consists of the padded bits, which is 1 followed by the required number of zeros, and then we compute a prefix free encoding of this padded message m dash under the key k2. Once we have the prefix free encoding of the message, we now operate the blockwise secure PRF FCBC under the key k0, and that is taken as the overall outcome of your PRF F star for the input m. So, here the keys k0, k1, k2 they are derived from the master key k with which you are going to operate your PRF F star by a subkey generation algorithm, which will be publicly known, and depending upon whether your message size is some constant times n or not, the prefix free encoding is operated with either key k1 or with the key k2. So, that is an indication to the receiving side whether the message which has been evaluated by this PRF F star, its size is already some constant times n or not. Now, the goal here is we want to construct a message authentication codes again for arbitrarily long messages, but now using a collision resistant hash function and a fixed length MAC. And we hope that indeed if we have one such construction, then we can completely get rid of the large number of PRF invocations which are used in this construction F star, right. So, let us see how we can design a message authentication codes for arbitrary long messages using a collision resistant hash function, and this paradigm is popularly called as hash and MAC paradigm. So, as the name suggests, what we do is if you are given an arbitrary length message on which you want to compute the authentication tag, then the tag is computed in 2 stages, and remember that our tag should be of fixed length. Its length should not depend upon the message which you want to authenticate. So, this fixed length tag is computed in 2 stages. In stage 1, we first hash the arbitrary message on which you want to compute the tag to a fixed length string, and this is done using a collision resistant hash function. And now once you have the hash of the message or the digest of the message which you have obtained in step 1, what we do is we compute the tag on the output which we have obtained on the previous step by using some fixed length message authentication code, and that is why the name hash and MAC paradigm. We hash first the input and then we compute a tag on the output of the hash of the message. So, block wise what you are given here is you are given a message authentication code which I denote by say pi MAC, and which is a secure MAC which has a key generation algorithm, tag generation algorithm and tag verification algorithm, and it can authenticate fixed size messages, namely messages of size say little l bits, and it has its own message space, key space and tag space. And we are also given say a secure or collision resistant hash functions say h taking arbitrary length inputs and giving you fixed size outputs, say outputs of size little l bits. Then what we are going to do in this hash and MAC paradigm is we are going to combine these two primitives and obtain a secure MAC which I denote as pi tilde, and it will have its key generation algorithm, tag generation algorithm and tag verification algorithm. The key space of this combined of the MAC that we obtain by composing the fixed length MAC and the collision resistant hash function will be the same as the key space of the fixed length MAC, whereas the message space will be strings or binary strings of arbitrary length, and the tag space will be the same as the tag space of your fixed length MAC pi MAC. So, here is how we compose the fixed length MAC along with the collision resistant hash function to obtain the message authentication code pi tilde. So, the tag generation algorithm is as follows. So, it takes a message which could be of any length, it is an arbitrary bit string and a key k randomly generated by the key generation algorithm. So, just to stress here, the key generation algorithm of the composed MAC is the same as the key generation algorithm of your base MAC. So, if the base MAC outputs a uniformly random key of some fixed size, then so is the key generation algorithm of this composed MAC. So, key k little k is one of those keys and m is the message on which we want to compute the tag. So, what we do internally inside this tag generation algorithm is we apply the collision resistant hash function on your input m, and once we have the hash of the message which is say of size little l bits, we invoke the tag generation algorithm of our base MAC under the key k of the composed MAC, and the resultant output is considered to be the tag of the is considered as the tag generated by the composed MAC. The tag verification algorithm is similarly done here. So, imagine you are given an arbitrary length input m along with the corresponding tag and you want to verify it with respect to a key k. So, what we do is we recompute the tag on the message part of the input. So, that we do by performing the hash or computing the hash of the message, and then again once we have the hash of the message, we again perform or we compute the tag verification algorithm with respect to the input h of m and the tag component of the input that you have received for this tag verification algorithm. And what we do is we invoke the tag verification algorithm of our base MAC with respect to the key k, and if the tag verification fails, that means this message comma tag pair should be rejected, whereas if the tag verification of the base MAC is successful, then that means we should accept the message comma tag that we have obtained for the composed MAC. So, that is how the hash and MAC paradigm works. So, now we want to analyze whether indeed this hash and MAC paradigm is going to give us a secure message authentication code for authenticating arbitrary length inputs. So, what we want to prove here is that if the component wise the fixed length MAC is a secure MAC, say CMA secure or strong CMA secure, and if the H component that is given to us is also a collision resistant hash function, then the composed MAC that we have obtained is indeed a secure MAC which can authenticate arbitrary length inputs. So, for simplicity what we are going to prove is we are going to prove the CMA security of the composed MAC, assuming that the base MAC is also deterministic, but that need not be the case. If your base MAC is a randomized MAC, then the overall MAC that we are obtaining is also a randomized MAC, in which case we should go for strong CMA security. But just to keep our argument simple, we assume that the base MAC is a deterministic MAC, and hence the composed MAC is also a deterministic MAC, and hence we are going to prove the CMA security. So, just to recall how exactly the CMA game will be played in against this composed MAC. So, as per the rules of the CMA game, adversary is going to ask for tags on several messages of its choice adaptively, namely polynomial number of messages, and to respond to adversary's queries, the challenger or the experiment runs the key generation algorithm, obtains a uniformly random key, and it computes the tag on all the messages for which the adversary has asked for the tag, and those tags are returned back to the adversary as per the tag generation algorithm of the composed MAC scheme. And finally, the adversary outputs a forgery, namely a message comma tag pair, and we say that the adversary has won the game or the output of the experiment is 1 if this message M star which has been submitted by the adversary is different from all the messages for which the adversary has asked for the tags, and the tag verification of the composed MAC on the M star comma T star gives you the output 1. So, our goal is to show that if the component wise the base MAC is secure and the underlying collision resistant underlying hash function is collision resistant, then the probability that any polytime adversary could win this experiment is upper bounded by some negligible probability. So, the idea behind the proof is as follows. So, if at all there exists an adversary who can come up with a forgery M star comma T star in polynomial time, then there could be two possible cases. The first case could be that the adversary who has come up with the forgery M star comma T star, for him it so happened that there exists at least one of the messages for which he has asked for the tag, such that which we denote as say by M, such that the forged message M star, even though that is different from that particular special message M, it so happened that the message M comma M star constitutes a collision for your underlying hash function. If that happens, then in that case it is easy for the adversary to come up with a tag on the message M star, because adversary has already queried for the tag on the message M and say it has obtained the tag T, and if the hash of the message M and the hash of the message M star are same, that means the tag for the message M star and as per the composed message authentication code will also be T, and hence by knowing M comma T it will be easy for an adversary to come up with the tag on the message M star, and that will be the forgery for the adversary. But this internally means that the adversary needs to find out a collision for the underlying hash function in polynomial amount of time, which contradicts our assumption that the underlying hash function is a collision resistant hash function, right. So, this is one of the cases by which, or one of the possibilities under which the adversary could come up with the forgery M star comma T star. The second case could be that it may so happen that the message M star, its hash is different from hash of all the messages for which the adversary has asked for the or queried for the tag. But even if the hash of the message M and the hash of the messages M star are different, it may so happen that the adversary is able to actually forge a tag on the fixed length input, namely hash of the message M star. If that is the case, then again adversary, whatever forgery M star comma T star adversary has submitted, it will be considered as a valid forgery. But for this case 2 to be true, what adversary basically has to do, it has to basically forge a tag on the message H of M star, where H of M star is different from all the H of M's for which the adversary has asked for the tag as per the composed scheme. But this will contradict our assumption that the base message authentication code that we are assuming is CMA secure. So, these are the two possible cases under which the adversary, an arbitrary adversary against a composed scheme, could come up with a forgery. Now, what we are going to formally establish is that both this case 1 and case 2 are going to be successful for any polytime adversary only with some negligible probability, right. So, formally here is your CMA game against the composed message authentication code for arbitrary length messages against an arbitrary polytime adversary. So, it asks for the tags for certain number of messages, and the set of those messages I am denoting by this fancy Q set, and in response it obtains the tag on those messages as per the unknown uniformly random key picked by the key generation algorithm, and as per the syntax of this composed scheme, each of this tag Ti is basically obtained by first hashing the message Mi and then computing a fixed length tag under the unknown key K on the hash of Mi's. And after obtaining the tags for this Q messages, adversary submits a forgery, and our goal is to analyze what is the success probability of this experiment or of adversary winning this experiment, which we denote by that CMA experiment outputting 1. And just as per the rules of the game, the CMA experiment outputs 1 if and only if the forged message M star is different from all the messages in the fancy key set, and the tag verification with respect to the unknown key for this message M star with respect to the tag T star is successful. So, to analyze the success probability of this CMA experiment, let me call an event call COLL, which basically denotes the event that there exists at least one message in the set of messages for which the adversary has asked for the tag, such that the hash of that message M is the same as the hash of the forged message M star. And now it is easy to see that the success probability of the adversary against this CMA experiment, or the probability that the output of the CMA experiment is 1, can be splitted into two disjoint events, namely conditioned on the event whether the event collision happens or not, right. So, the overall probability that the output of the CMA experiment is 1 can be written as the probability that the output of the CMA experiment is 1 and the event collision occurs, plus the probability that the output of the CMA experiment is 1 and the collision event and the event collision does not occur, right. So, this follows from the basic rules of probability, and now what I can do is this first term here, I can always upper bound it by the probability of the event collision to happen, and the remaining probability I am retaining as it is, right. So, just I am doing some substitutions here. So, I can always upper bound the probability that the output of the experiment CMA is 1 by this entity. And now what we are going to show is that each of these expressions on your right hand side, namely the probability of the event collision to happen and the probability that the output of the CMA experiment is 1 and the event collision does not happen, both are negligible functions of your underlying security parameter. So, let us establish these two facts one by one. So, both of these facts we are going to establish through a reduction proof. So, what we are going to do is assume we have an arbitrary adversary who can forge your MAC, or who can submit a forgery against the combined or the composed MAC, and using that our goal is to find or create another polytime adversary, this fancy C, whose goal is to basically find a collision in the underlying collision resistant hash function. So, what basically do is we do here in the reduction is the adversary or the MAC forger asks for tag on several messages of its choice, say q number of messages, and to respond to those queries, what this collision finder algorithm does is it runs the key generation algorithm of the composed MAC itself, generates a uniformly random key, and it computes the tag on the messages for which our MAC forger has asked for the tag, and the response are given back to the MAC forger. And as per the syntax of the composed MAC, each of this TI is basically computed by first hashing the message as per the underlying hash function H, and then computing a fixed length tag on the hash of each MI under the unknown key K. So, if we see what is happening in this reduction is from the viewpoint of this MAC forger, right, if we consider this MAC forger, right, the probability distribution of the information that it is receiving from this collision finder is exactly the same as this MAC forger would have expected by participating in a real instance of the CMA game against the composed MAC, because in a real instance of the MAC CMA game, what basically the adversary would have done, it would have submitted several messages of its choice, and the tags that it would have seen in response would have exactly the same distribution as provided by the collision finder algorithm to this MAC forger, right. So, view wise, the probability distribution of the information that the MAC forger is seeing in this reduction is exactly the same as this adversary would have seen in a genuine instance of the CMA experiment. After getting the tags on the messages of adversary's choice, basically this adversary or the MAC forger outputs a forgery. And what is the goal of the collision finder? The goal of the collision finder is to find out a collision in the underlying hash function. So, what it does is it basically parses the set of messages in the query set. So, it has the set of messages for which the adversary has asked for the tag, and it parses those messages and sees if there exists at least one such message MI in that set, such that the message mi is different from the forged message m star, and the hash of that message mi is same as the hash of the message m star. If that is the case, then this collision finder algorithm outputs a collision for the underlying hash function h. And it is easy to see that the running time of this collision finder algorithm is polynomial time if the running time of the MAC forger algorithm is a polynomial time, right. So, now it is easy to see that the probability that the collision finder successfully outputs a collision is exactly the same with which the event collision happens when this adversary MAC forger participates in an instance of the CMA game. Because if indeed the event collision happens, that means there exists at least one message mi which is different from m star, but the hash of m star is same as h of mi, then in indeed that case the collision finder algorithm will be able to successfully find the collision. And the event that mi different from m star, but their hash values are same is nothing but the event collision. So, since I am assuming that my underlying hash function is a collision resistant hash function, then it, as per the definition of collision resistant hash function, this probability should be some negligible function of the security parameter. And since that probability is the same as the probability of the event collision happening, that means the event collision also happens with some negligible probability. So, that established the first fact that we wanted to establish. Now, let us establish the same fact, namely we want to prove that assuming that the event collision does not happen, the probability that the MAC forger algorithm against the composed MAC can win the CMA game is upper bounded by some negligible function, and that we establish by giving a reduction. So, we assume that we have a polytime adversary MAC adversary who can forge who can break the security or the CMA security of the composed MAC. Now, using that adversary, we design another adversary which we denote as say A dash, and its goal is to actually create a forgery against the fixed length base MAC. So, now what this adversary for the composed MAC does is it participates in an instance of the CMA game against the composed MAC, and as per the rules of the CMA game, it asks for the tags for several messages of its choice. What this adversary A dash now does is it invokes an instance of CMA game against the fixed length MACs, where the messages which are authenticated are of fixed length, namely little L bit messages, right. So, the difference in the CMA experiment here and the CMA experiment here is the length of the messages. In the CMA experiment against the composed scheme, each of these messages M1, M2, MQ, they could be of any length. But in the CMA game placed against a fixed length MAC, the query set can consist of only messages whose lengths are of little L bits. So, what this adversary A dash does is it plays a dual role. On your left hand side, he is actually acting as an adversary, and its goal is to win an instance of CMA game against a fixed length MAC, but on the right hand side he is acting as a verifier, right, and is interacting with the MAC forger against the arbitrary length inputs. So, what this adversary A dash is now doing is it got a set of queries on which it is supposed to create tags as per the composed scheme, and to do that what it does is it hashes all those messages, and though the hash of those messages are supplied as a query set to the verifier in the CMA game against the fixed length MAC. Basically, adversary A dash is asking now for the tags on the hash of these messages M1, M2, MQ. And as per the rule of the CMA games, as per the rules of the CMA game, the verifier of the CMA game against the fixed length MAC generates a key, and it responds back by computing a tag on hash of each of the messages which has been submitted by the adversary A dash, right. Now, what this adversary A dash does is it has to respond back to the queries which the adversary A has raised to the adversary A dash. So, what it does is it supplies the same response to the MAC forger as it has received from the verifier in the CMA game against the fixed length MAC. So, again before proceeding further, let us understand what is happening here. If we consider the view of the adversary A against the composed scheme, the view is exactly the same as this adversary would have seen by participating in a genuine instance of CMA game against the composed MAC. Basically, he would have submitted any messages of his choice, and in response he would have seen tags where the distribution of the tag will be exactly the same, that namely it will be the tags will be computed by first hashing the messages. So, that is why the hash of the messages are supplied by the adversary A dash here, and once the hash of the messages have been computed, a fixed length tag would have been obtained on the hash of those messages, and that is what will be the distribution of the tag values that the adversary A would have seen in the composed MAC, and that is what exactly is happening in the reduction. So, as for the view of the adversary A is considered, its view is exactly the same as it would have expected by participating in a genuine instance of the CMA game against the composed MAC. So, what this adversary A does now does, it submits a forgery against the composed MAC, say M star comma T star, and what the adversary A dash has to now do is it has to create or it has to output a fixed length forgery for the fixed length MAC base MAC, right. So, what it does is basically whatever forgery M star comma T star has been submitted by our adversary A, the adversary A dash computes a hash on the message M star, and that is the message on which it is creating a forgery, and the corresponding forged tag is T star. So, now it is easy to see that what is the probability that our adversary A dash which we have created here is able to win the CMA game against the base MAC or the fixed length MAC. Well, the probability that it can win the CMA game against the fixed length MAC is exactly the same as the adversary A wins the CMA game against the composed MAC and the event collision does not happen in the instance of the experiment. Namely, if the event collision does not happen, that means the hash of all the messages M1, M2, MQ, they are different from the hash of the message M star. That is precisely the event collision not happening, and adversary A still winning the game, right. If adversary A still wins the game, that means the message M star comma T star is indeed a forgery even in the presence of the event negation of collision, then indeed the hash of the message M star comma T star is a valid forgery for your fixed length MAC, which will give which will imply that the adversary A dash has won the CMA game against the fixed length MAC. Now, since we are assuming that our base MAC or the fixed length MAC pi MAC is secure, then this quantity is a negligible quantity. Namely, there exists no adversary A dash who can win the CMA game against the fixed length MAC with probability better than negligible probability in some security parameter. That means the other event, the event on your right hand side, namely the adversary or the MAC forger winning the CMA game against your composed MAC in the presence of the complementary event collision, also occurs with some negligible function in the security parameter. So, this proves the two facts that we wanted to state, and this overall shows that the hash and MAC paradigm is indeed going to give you a secure MAC for authenticating arbitrary long messages. So, now we have a generic paradigm, namely hash and then MAC paradigm. So, what we will do is that we will see an instantiation of this paradigm which we call as HMAC, and basically the motivation of this HMAC construction is that we want to create a MAC which is just based on hash functions, right. So, if you see the hash and MAC paradigm, it uses two cryptographic primitives, namely it uses a cryptographic collision resistant hash function as well as it uses a fixed length MAC. Whereas the HMAC instantiation that we are going to see for the hash and MAC paradigm, it is an industry MAC standard, and the advantage of this HMAC construction is that it just involves hash functions, everything just based on hash function. You do not require another primitive, namely a fixed length MAC. And let us see how exactly we construct this HMAC. So, what we are given here is we are given a collision resistant compression function which takes an input of size n plus l bits and gives you an output of n bits, and it is provably secure and it is collision resistant. So, for concrete instantiation of such a compression function, you can take the Davis-Meyer construction which we had discussed in the last lecture, whose security we have proved in the ideal cipher model. So, pictorially this is how your Davis-Meyer function will operate. It takes an input of size n plus l bits, but that input of size n plus l bits you can imagine as if it contains of two chunks of inputs or two parts of input, one part of little l bits, another part of little n bits, and overall the output is the fixed size output of n bits. And we had seen in the last lecture that if Davis-Meyer construction you can instantiate using any secure block cipher, say AES, DES and so on. So, what this HMAC does is basically it has two layers of several iterations of this Davis-Meyer construction, and overall it is controlled by a key, right, because remember we want to design a MAC. So, we have a key for the MAC. So, these two layers of the several iteration of the Davis-Meyer construction is controlled by a key, and finally we obtain a tag. So, what exactly these two layers are, right. So, the layer 1 is an inner layer, and what it does, it takes the arbitrary input on which you want to compute the tag, and it creates a fixed length output of that input on which we want to compute the tag as per the Merkle-Damgard transformation, but iteratively applying this Davis-Meyer function several times. And remember, the output of the Merkle-Damgard transformation gives you a fixed length output. Once we have the layer 1, what we do in the outer layer is we actually compute the tag on the output that we have obtained from the inner layer, and this again is done interestingly by using one instance of the Davis-Meyer function. So, that is the difference here, right. So, even though this can be viewed as an instantiation of your hash and MAC paradigm, because we are first hashing the message and then we are creating the tag on the message, the interesting part here is that the tag for the message is also computed using an instantiation of one instance of the Davis-Meyer function or the collision resistant compression function. We do not need a separate MAC for this second layer. So, let us see the architecture of the HMAC. So, we have some publicly known constants here which we denote as IPAD and OPAD. IPAD basically stands for input pad and OPAD stands for output pad, each of length little l bits, and we have a secret key of little l bits which is the master key for the overall MAC that we want to construct, right. So, what we do is we invoke one instance of the Davis-Meyer construction where the overall input is of size n plus l bits. The message part is basically the XOR of the IPAD with the key, and we have a fixed publicly known IV, and then what we do is we actually apply the Merkle-Damgard transformation. So, what we have done basically here is you have the message M on which you want to compute the tag for the message under the key K. So, what we do is this part is basically, right, inner layer of hashing, where this inner layer of hashing, this part is nothing but a Merkle-Damgard transformation, where we would have encoded the message and then the last block we would have added some padding bits which basically denotes the binary representation of the number of little l bit blocks which are present in your message, and then we would have done a sequence of chaining where in each iteration we will have one invocation of your Davis-Meyer function on the current block of the message and the output of the previous invocation of HDM. The difference here is that the IV now here is an IV or a key value which is obtained by running one invocation of the Davis-Meyer function on this input K XOR IPAD with a fixed known IV. So, this is your inner layer of hashing, and it will give you a fixed size output. And what we do in the MAC part or the outer layer is the following. We take the output T which is of size say little n bits, and little n might be less than little l. So, what we do is we do the padding here, and we do two invocations of the Davis-Meyer function here, where the first invocation is now with the XOR of K with OPAD, and whatever output comes, it is used as a key, right, or it is used as one of the inputs along with the tag concatenated with the output pad being input, and whatever output comes out, that is taken as the overall output of the HMAC construction for your message. And this second layer actually is the outer layer of the message authentication code. So, you have the inner layer of hashing where we take the arbitrary length message, compute a fixed length tag, and then we take that fixed length tag and then again do two invocations of the Davis-Meyer function to compute the final MAC. So, now we will not go into the full fledged security of this HMAC construction, but let us intuitively try to understand what is happening here. So, this is the overall architecture of the HMAC construction. So, what we are doing here is we are actually deriving two keys by running the Davis-Meyer function. Here you can call those keys as K in and K out, right, and K in is basically serving as the IV for your the Merkle-Damgard transformation, whereas the k out is serving as the one part of the input for the Davis-Meyer function when we are actually computing the tag. So, imagine that we define a function g which takes a key k for the overall MAC and it invokes Davis-Meyer function twice like this. Sorry for this typo, this should be dm should come in the subscript. So, we have two invocations of the Davis-Meyer function. The first invocation is on input IV concatenated with the XOR of k and IPAD, and the second invocation is on the input IV concatenated with k XOR OPAD, and say the resultant output is k in and k out, right. Interestingly, what we can prove is the construction g of k that we have defined like this, it is like a pseudo random generator if we go in the ideal cipher model. So, in the original pseudo random in the security definition of the pseudo random generator, the game was that the adversary is given a challenge sample and it has to distinguish whether the sample is generated by the pseudo random generator or a true random generator. But if we take that game in the ideal cipher model, then apart from the challenge sample which is given to the adversary has also got oracle access to the underlying block ciphers which are used in the instantiation of the Davis-Meyer function. And based on oracle access to the underlying block ciphers which are used in the Davis-Meyer function, the goal of the adversary is to distinguish the challenge sample whether it is truly random or whether it is pseudo random. So, we can formally prove that a construction g of k that we have defined like this indeed is a pseudo random generator in the ideal cipher model, and that means what? That the distribution of the two keys that we have obtained, namely k in and k out, which we are using in the inner layer and the outer layer, their distribution is indistinguishable, computationally indistinguishable from a distribution of truly random keys k in and k out that would have been obtained by running a true random generators. So, that means you can safely consider this k, the keys derived keys k in and the derived key k out to be as good as true random keys. Now, let us focus on the inner layer of the hashing, right. So, again sorry for the typo here, this should be h of h sub md. So, basically this denotes the Merkle-Damgard transformation. So, what we are doing in the inner layer of hashing is basically a Merkle-Damgard transformation on the input k in concatenated with the encoded m. The only difference now is instead of a fixed IV which is all zeros in the case of the Merkle-Damgard transformation, the IV with which we are triggering the Merkle-Damgard transformation is a derived key k in, right. So, you can imagine in some way that the whatever function that we have computed by applying the Merkle-Damgard transformation on the encoded input and the concatenated with k in, that is kind of define a keyed hash function which I denote as h tilde, right. And we can prove that this function h tilde k in constitutes a collision resistant hash function even if adversary has seen polynomial number of outputs of this keyed hash function for several messages of its choice. So, we can formally establish this, that is very simple, but for but due to lack of time I am not going into the formal details. So, what it means is even though we are doing a Merkle-Damgard transformation during the inner layer of hashing controlled by a key k in, that constitutes a keyed hash function which can be formally proved to be collision resistant even if adversary has oracle access to that keyed hash function. That means whatever output t that we are obtaining here, that you can consider as an outcome of a collision resistant hash function, right. So, that is what the first part of the security overview of the security proof. The second part is with respect to the MAC part or the fixed length MAC part that we are computing here. So, imagine that I define a tag generation algorithm, again sorry for the typo here, it should be h sub dm, which basically is one instantiation of the Davis-Meyer construction with a key as input and the message as also concatenated with the message also as the input, right. So, that will be the overall tag generation algorithm for the message m under the key k. So, basically the part that I have highlighted here in the under the box, that is nothing but the outcome of this tag generation algorithm. That means you can imagine that this t dash that is coming is a output of a tag generation algorithm and we can correspondingly define a corresponding tag verification algorithm. And interestingly, we can prove that the way this Davis-Meyer function is operating here, in the ideal cipher model we can consider this instantiation of Davis-Meyer function to be a secure MAC for fixed length inputs. So, if that is the case, then the output T dash that we are obtaining here, it can be considered as the tag for the message T concatenated with padded bits under the key K out, and as per our assumption the key K out is computationally indistinguishable from a uniformly random key. That means we can imagine that the T dash is an outcome of a fixed length MAC. So, overall what we can imagine is that even though everything involves instantiation of the Davis-Meyer construction, overall this HMAC can be considered as an instantiation of your hash and MAC paradigm, because the first part, namely the inner part, is nothing but doing a keyed hashing for the message as per the Merkle-Damgard transformation, where the key is computationally indistinguishable from because it is derived from one invocation of the Davis-Meyer function, which in the ideal cipher model we can prove to be equivalent to a pseudo random generator. And the actual message authentication code, right, this part is basically a keyed invocation of Davis-Meyer function on the output that we are obtaining from the hashing stage. And again, in the ideal cipher model we can prove that the instantiation of this Davis-Meyer function as per the key, where the key K out is computationally indistinguishable from a uniformly random key, gives you a message authentication code which cannot be forged. So, as a result we can view this overall construction of HMAC as an instantiation of the hash and MAC paradigm, and as we have stated earlier, the hash and MAC paradigm is indeed secure if your underlying hash function is collision resistant and if your MAC is a secure MAC for fixed length messages. The only difference in the proof is that the underlying components are secure in the ideal cipher model, namely the keyed hash function is collision resistant in the ideal cipher model, and the underlying fixed length MAC is also can be proved to be a secure MAC in the ideal cipher model, and that implies overall that HMAC is secure. And this is really one of the highly popular instantiation of message authentication code which is used in practice. So, that brings me to the end of this lecture. Just to summarize, in this lecture we have seen the hash and MAC paradigm, which is the generic construction and which gives you a message authentication code for arbitrary long messages by combining or composing a MAC for fixed length messages and a collision resistant hash function. And we had also seen an instantiation of this paradigm, namely the construction of the HMAC message authentication code. Thank you.